Friends, today in the 11th lecture under the NPTEL course on offshore structures under special loads including fire resistance, we will continue to discuss about some details and complexities related to wind loads. As we discussed in the last lecture, wind loads vary both in space and time. We also said that if I have a wind load which is measured as a variation in time and I call this as total wind velocity, and if it varies along the time as you see here, this can be equivalently said as a wind velocity with a static component what we call V 0 and the dynamic component which varies with time which we call as the gust component. Therefore, V can be said as V bar plus V of t, where V bar is the mean wind velocity and V of t is the gust component. We also said in the last lecture that gust factor can be used to account for the variations which can be considered equivalent to compute the gust load. A gust factor of about 1.35 to 1.45 is a normal recommended value for design of offshore structures. So, one can always estimate the fastest mile velocity which is actually equal to the sustained wind speed multiplied by the gust factor. The sustained wind speed for a 100-year return period is taken as 125 miles per hour. So, to account for the spatial variation and time, we also said that the gust component variation is very minimum. Hence, people use what we call aerodynamic admittance function to find the equivalent total load on the structural members caused by wind. We clearly understand that wind has got two components. One is the steady wind or the mean wind velocity component, and other is a time varying component which is the gust factor or the gust component. To account for both of these at one given point of time, people use aerodynamic admittance function. There are essentially two reasons why do we use aerodynamic admittance function. One, we wish to bypass the rigorous random vibration concept. Secondly, aerodynamic admittance function can be measured experimentally. One can conduct wind tunnel experiment to measure aerodynamic admittance functions. It means aerodynamic admittance function can be quantified with better accuracy. Force in wind is actually half rho C d A V square, equation 1, which is half rho C d A. V square is actually V bar plus V of t, the whole square. Expanding this, let us say half rho C d V bar square V of t square plus 2 V bar V of t. Since V bar is much higher than V of t, we can neglect higher powers of V of t. Therefore, F t can be said as half rho C d A V bar square plus 2 V bar V of t. Expanding half rho C d A V bar square plus rho C d A V bar V of t. So, this component is called steady mean drag force. This component is the fluctuating zero mean force. So, now I can say this as F bar omega plus F g, where the gust component is rho C d A V bar V of t. So, let us say consider a 6 single degree freedom system model. Let us say I have a model attached with some stiffness spring K and some damper C, and there is a mass attached to this. The mass has an exposed area A. Now, the mass undergoes a static displacement x s, which is called the static displacement, and from this point it undergoes a dynamic response. So, this is the dynamic response which is x of t. So, static displacement we know is actually d bar by k. So, I can now say the total response could be static response plus k of V of t, which is actually the dynamic response. Interestingly, V of t is handled as a random process. Strictly speaking, it should be handled as a random process, but for simplicity this can be modeled as deterministic process. So, some simplification is done to handle the gust part. We also know that we are considering wind load as ergodic. We already said in the last lecture what do we understand by ergodic. So, therefore, once we say it is ergodic and acceptable, let d of t happens to be the single time history, that single time history which can represent the ensemble. Let us say typical time history is this way, with an arbitrary time history. Therefore, the power spectral density function which is one sided of the wind process f t is related to the wind spectrum as below. S f plus omega is rho C d A V bar square of S u plus omega. This is actually u. This is the force, this is the response. By simplification, S f omega can be now said as 4 f bar omega square. I am taking the mean wind component by V bar square of a chi function of omega root A by 2 pi V bar the whole square of S u omega Interestingly, let us look at the property of this particular function. The particular function looks like this. For omega, I want to plot chi square omega. So, that is how the plot looks like. This is unity. So, it means chi of omega root A by 2 pi V bar tends to 1 when omega root A by 2 pi V bar tends to 0. That is what you see here. When omega root A by 2 pi V bar tends to infinity, the chi function tends to 0. So, that is the characteristic of this function. This function is called the aerodynamic admittance function. Davenport in 1977 proposed an aerodynamic admittance function by an empirical equation. He says chi of the variable can be simply 1 by 1 plus 2 x to the power 4 by 3. So, the advantage or let us say the advantages with aerodynamic admittance function is, it actually simplifies the random process of wind load, because by using the aerodynamic admittance function you are not involving the gust component and the complexity in estimating the wind forces. 2, this function can be estimated, I should say rather computed significantly to a better accuracy experimentally. So, use of aerodynamic admittance function converts the complexities in random process of wind loading to somewhat more or less a simple problem of a deterministic load. So, based on this, wind spectra are recommended for offshore structures. Like we saw wave spectra, wind spectra also recommended for design of offshore structures. There is a fundamental understanding of wind spectra compared to wave spectrum. Wind spectra is generally expressed in terms of circular frequency. Further, SU omega is f of, let us say, GUF. The reference height for estimating the wind force, let us say the mean wind velocity is 10 meters. So, Davenport has given a spectrum which is Davenport spectrum. It says that omega S omega by del U 10 square is actually equal to 4 theta square by 1 plus theta square 4 by 3. Harris also given a spectrum. It says omega SU omega by del U 10 square is 4 theta by 2 plus theta square 5 by 6, whereas theta is a dimensionless variable which is given by theta is equal to omega Lu by 2 pi u bar 10, which otherwise 2 pi by omega is actually f, which is Lu by u bar 10, where 0 less than theta less than infinity. In this case, Lu is called integral length scale, which is actually 1200 meters for Davenport spectrum and it is 1800 meters for Harris spectrum. Delta is called the surface drag coefficient, referred at U10. Usually this value is taken as 0.001. So, del is usually 0.001. One fundamental complexity what we have in all these spectra designed and recommended for offshore structures is that none of the above spectrum is derived originally for analysis of wind speed on offshore structures. Then one may ask me a question, they are derived for what kind of structures? They are derived for land based structures. So, this can be seen as one of the important complexity which may arise in inaccurate estimates of wind forces on offshore structures. So, this can lead to further complexities. What are those complexities? Application of these spectra to offshore structures can be questionable. That is the first thing we have. The second issue we have is something structurally related. These spectra have serious problems. These spectra have serious problems when used for low frequency flexible structures. This is the catch, because we are discussing about hybrid structures where there are two set of frequencies, one is extremely low with a very high period, other is extremely high with a very low period. So, when we have a structure which is flexible, what we say is compliant, with a low frequency dominance in its response vibration characteristics, using these spectra will have problems. Alternatively, other researchers have given alternate spectra for computing wind forces on offshore structures. For large floating structures, considering the flexibility order of the structural system, chimal spectrum was proposed. So, chimal spectrum as recommended by Derby and Hansen in 1997 is an alternate spectrum used for large offshore structures. This says that omega S omega by sigma u square will be 6.8 theta by 1 plus 10.2 theta raised to the power 5 by 3. Let us call this equation number 1, where sigma u square is the variance of u of t at reference height of 10 meters. The second spectrum comes in line for large floating structures, is given by American Petroleum Institute in 2000, omega SU omega, but I should say sigma u z square is actually equal to omega by omega p, that is the ratio 1 plus 1.5 omega by omega p, the whole raised to the power 5 by 3, where sigma square u is a variance of the gust component. The only interesting part is this is assumed to be independent of reference height. In the earlier case, if you see, this is actually measured with reference to 10 meter height, whereas in this case it is a function of z itself. Omega p is called peak frequency, which can be estimated by the relationship 0.01 less than equal to omega p z by u bar z less than 0.1. Usually a typical value of 0.025 is chosen for the design. In that case, standard deviation of the wind speed is given by actually equal to 0.15 u bar z Zs by z to the power 0.125 for z less than Zs. Otherwise, it is equal to 0.15 u bar z Zs by z to the power 0.275 for z greater than Zs, where Zs is called thickness of the surface layer usually taken as 20 meters. So, one can very clearly see here API and Davenport fundamentally differ by estimating or fundamentally differ in estimating u bar z of sigma. So, Davenport says it is at z equal 10 meter, whereas APA says there is a ratio of Zs by z, where Zs is 20 meter and z is the height where you are considering your calculation. So, typically if you try to plot the spectra, let us say 10 power minus 2, 10 power minus 1, let us say 1 and 10 power 1, I am trying to plot theta, whereas in this case let us say 10 power minus 1, let us say 1, let us say 10, 10 square, let us say 10 cube. This I am plotting SU omega versus theta. This is the plot, or I should say plots of wind spectra. Typical APA spectrum starts from here and goes this way. This is my APA spectrum. Whereas the Harris spectrum starts from here and follows similarly the same path as of API. This can be Harris spectrum, but Davenport has a small variation. It starts from 1, takes the peak somewhere here in between, and then it goes in between with these two. So, I should say this is Davenport. Please note, in the above, theta actually is omega Lu by 2 pi of u bar 10 for Davenport and Harris, whereas this is equal to omega by omega p for API, because API actually does not calculate the variance based upon U10, but depends upon surface layer thickness, which we saw in the last slide. So, there is a very important observation we can make by looking at these spectra. All the 3 spectra or all the spectra vary significantly at low frequency. You can see here, when the frequency is lower, the variation is significant. So, this can influence wind induced response of flexible structures. Essentially, when the structure is moved or tethered, which derives strength from buoyancy, those structures can be very critically affected. So, friends, we have discussed conventional loads like wave loads. We have also discussed wind loads. We also said they are randomly varying, but they can be idealized as a Gaussian process. Therefore, one can make some simplifications to convert them to equivalent quasi static loads as in the case of wind loads by using aerodynamic admittance function, and one can estimate more or less the influence of the gust factor or the gust component on the overall response of the structural system by adding it indirectly, which includes the spatial and the time variation in the loading to get the response of the platform under wind loads. However, in the last lecture we saw the complexities that arise because of the wave loads, which essentially comes from 3 factors: the spatial variation, the time, and the wave directionality, essentially the wave height or the amplitude, the period, and the wave direction. So, one is interested to know what is that phase lag or angle of attack of the wave where the drag and inertia components both are maximum at any given time. We also showed you how, interestingly, the phase lag can be used to cancel the forces on the offshore members, which depends upon to decide what should be the spacing of the legs of the members, essentially the form dominated geometric design of complaint offshore.